Hello, welcome to another module in this massive open online course. So, we are looking at the Laplace transform and looking at the Laplace transform, the various properties of the Laplace transform, the concept of the region of convergence, and the Laplace transform, the impulse and the unit step functions. Let us now look at the Laplace transform, the cosine function. Okay. So, we have looked at the Laplace transform of the unit impulse and the unit step function. So, let us continue looking at the Laplace transform of some common functions. So, Laplace let us continue looking at the Laplace transform of some common functions or some common signal. Let us look at the Laplace transform in particular of cosine signal. Okay, so this is your cosine signal and the Laplace transform and cosine t ut, cosine omega naught t times the unit step function. So, the Laplace transform of cosine omega naught t ut, this is equal to integral, because of the ut it is non-zero only for t greater than equal to 0. So, this is equal to 0 to infinity cosine omega naught t e power minus st dt, which I can write as cosine omega naught t, I can write as half e raised to minus j omega naught t plus e raised to j omega naught t, correct, e raised to minus j omega naught t plus e raised to j omega naught t, e raised to minus st dt, which is equal to, well, half integral 0 to infinity e raised to minus s plus j omega naught t dt plus half integral 0 to infinity e raised to minus s minus j omega naught t dt. Okay. So, I have written it as the sum of two integrals. So, this is the first integral is, well, this is e raised to minus s plus j omega naught t divided by minus s plus j omega naught evaluated between the limit 0 to infinity plus half e raised to minus s minus j omega naught t divided minus s minus j omega naught evaluated between the limit 0 to infinity. So, this is half of 1 over, now if you evaluate this between the limits 0 to infinity, e raised to minus s plus j omega naught t evaluated as limit t tends to infinity tends to 0, but only if the real part of s is greater than 0. So, this is the region of convergence. Similarly, e raised to minus s minus j omega naught t tends to 0 as t tends to infinity only if s greater than, real part of s is greater than 0. So, this is basically your ROC. Okay. So, this is your real part of s greater than 0, that is the ROC, and in the ROC this is the first term is 1 over s plus j omega naught plus 1 over s minus j omega naught, which is equal to half 1 over s plus j omega naught plus 1 over s minus j omega naught, that is 2s divided by s plus j omega naught times s minus j omega naught, that is s square plus omega naught square, which is equal to s by s square plus omega naught square. Okay, so this is the Laplace transform. So to summarize, the Laplace transform of cosine omega naught t ut equals s square by s square plus omega naught square. I am sorry, s divided by s square plus omega naught square. So this is the Laplace transform of the signal cosine omega naught t ut. Now let us look at, and similarly you can compute the Laplace transforms of some other commonly occurring signals. For instance, you can try to compute, we have computed the Laplace transform of cosine omega naught t ut, you can try computing the Laplace transform of sine omega naught t ut, and similarly you can compute the Laplace transform of several other commonly occurring signals. Okay. Now let us look at some properties of Laplace transform, some of the interesting aspects of Laplace transform which indeed make it a very handy tool. Okay. So let us look at the properties of the Laplace transform. Some of the properties of the Laplace transform, for instance, if you have two signals x1t with Laplace transform x1s, x2t with Laplace transform x2s, then the Laplace transform is a linear transform. So Laplace transform of a1 x1t plus a2 x2t, this is a1 x1s, and you can easily show this is a2 x2s, because integral of a sum is the sum of the integrals. And but the only important point here is to look at the region of convergence, because remember we said the Laplace transform is incomplete without specifying the region of convergence. So the region of convergence of the first one is ROC, region of convergence is R1, second one region of convergence is R2, then the region of convergence of the linear combination will be the intersection, correct? So the ROC will be equal to R1 intersection with R2, because naturally both the Laplace transforms x1s and x2s have to exist. So x1x exists only in the region of convergence, that is defined for R1, x2s is defined for R2, and therefore the region of convergence of the sum will be R1 intersection R2, that is the intersection of these two regions of convergence. Okay, so that is something important to keep in mind. Okay. Now time shifting property, let us look at another important property, which is the time shifting property. What happens when a signal is the time shifting property of the Laplace transform, that is if Laplace transform of xt, that is if xt has Laplace transform xs, then what can you say about the Laplace transform of xt minus t naught, that is xt minus t naught is xt, remember this is xt delayed by this is a delayed version of xt, that is if you have xt which is something like this, which is a signal that looks something like, if xt is this signal, this point is 0. So if this is the signal xt, then xt delayed by t naught will look something like this, that is at this point is t naught. Okay, so this is shifted to the right by t naught. Now, what is the Laplace transform of the delayed signal, that is x t minus t naught? Well, for that I can perform the integral x t minus t naught e raised to minus s t dt, which is equal to, now I can set t minus t naught equals t tilde, which implies dt equals dt tilde. So, this will become, this integral will become equivalently integral 0 to well t minus t naught, or so this integral is from minus infinity to infinity. So, this will also be from minus infinity to infinity. This integral will be x of, I can write it as in terms of t tilde, x t tilde e raised to minus s t tilde plus t naught dt, which is, now I can bring out the e raised to minus s t naught outside, integral minus infinity to infinity x of t tilde e raised to minus t tilde d tilde, and this we know, this is basically the Laplace transform. This is the Laplace transform of x t, which is equal to x s. So, this is equal to e raised to minus s t naught times x s. So, basically the Laplace transform of the delayed signal x t minus t naught is e raised to minus s t naught x s, and you can see the region of convergence will be the same because we are directly using the Laplace transform x s. So, whenever x s exists, e raised to minus s t naught x s exists, as long as s is a finite quantity. Okay. So, basically the region of convergence will be region of convergence of Laplace transform of f t x t that is the region of convergence of x t, okay, or the Laplace transform of x t, and therefore we can say that x t minus t naught equals, or not equals, that is the Laplace transform of x t minus t naught is e power minus s t naught into. So, basically a delay in time domain. So, when we delay signal in time domain, this is equal to multiplication by e raised to minus s t naught in the Laplace domain or in the s domain. So, delay, and this is an important property. E raised to minus s t naught in the transform domain. So, x t minus t naught has the Laplace transform e raised to minus s t naught x s. Okay. Now, let us look at another aspect. What happens when you multiply in the time domain, that is, if you have x t, let us look at the other scenario, or when you have x t whose Laplace transform is x s, if you multiply this by e raised to s naught t, that is, if you multiply this by an exponential signal, then what is the Laplace transform? Okay. And to find this Laplace transform, we can perform minus integral minus infinity to infinity e raised to s naught t x of t e raised to minus s t dt, which I can write as integral minus infinity to infinity xt e raised to minus s minus s naught e raised to minus s naught t dt. And if you look at this, this is the Laplace transform evaluated at s minus s naught. So, this is x of s minus s naught, because look at this is x of t, integral x of t e raised to minus s naught t dt. This is the Laplace transform evaluated at s minus s naught, that is x of s minus s naught. So, this is Laplace transform evaluated at s minus s naught. However, for the region of convergence, now look at this convergence, if s minus s naught or real part of s, correct, real part of s, let us put it this way, this converges if this has ROC equals R, then we need, for this to converge, we need s minus or the real part of s minus or s minus real part of s naught belongs to R, which implies s belongs to R plus real part of s naught. So, this converges if s minus the real part of s naught belongs to the region of convergence of x t. Therefore, the region of convergence of e raised to s naught t x t will be real part, that is the region of convergence of x t plus the real part of s naught. So, this is the region of convergence. Okay. The previous region of convergence of x t plus real part of s naught, that is region of convergence of x t shifted by the real part of s. Let us look at another property, that is differentiation in time. That is differentiation in time, that is if x t has region of has x s, that is x Laplace transform x s, what can we say about dxt dt? What is the Laplace transform of this? To evaluate the Laplace transform of this, we have dxt over dt e raised to minus st dt, which is now if you apply integration by parts, integrate dxt over dt, that gives xt multiplied by e raised to minus ft xt minus integral 0 to infinity, I am sorry, integral minus infinity to infinity. Of course, this has to be evaluated between the limits 0 to infinity minus integral 0 to infinity x of t. In integration by parts, I have to differentiate d raised to minus st over dt dt. Now, if you look at this x t e raised to minus st evaluated between the limits, I am sorry, minus infinity to infinity, we can assume that the signal x t is such that x t evaluated at e raised to minus st, x t evaluated from minus infinity to infinity, that is x t into e raised to minus st evaluated at both infinity and minus infinity is 0. For instance, if x t is a signal, is a right sided signal that exists only for t greater than 0, then x t evaluated at x t e raised to minus st evaluated at t equal to minus infinity is 0, and x t similarly x t into e raised to minus st, since e raised to minus st is decreasing, correct. So, we can assume that x t into e raised to minus st evaluated at t equal to infinity is also 0. So, this term is 0 and we are left with the second term. So, that gives us integral minus infinity to infinity xt derivative of e raised to minus st dt, which is xt, correct. Derivative of e raised to minus st is basically minus s. So, minus s e raised to minus st dt, which is basically s times minus infinity to infinity xt e raised to minus st dt, and you can see this is the Laplace transform simply of xt. So, this is s times x of s, and the region of convergence will be the same because xs exists whenever the Laplace transform of xt exists. So, region of convergence is the same as that of the region of convergence of xt. Therefore, the derivative has the Laplace transform. If xt is Laplace transform capital Xs, the derivative has Laplace transform xs. Okay. So, the differentiation in time multiplication by s in the transform domain. Okay, this is equivalent to multiplication by s in the transform domain, ROC equal to R, which is equal to ROC of, this is the same as the ROC of xt. Similarly, you can show that, similarly you can explore other properties. There are several properties of the Laplace transform. So, you can explore, I believe some of these for you to explore. You can easily see that t x of t has Laplace transform minus dxs over ds. That is, if you multiply by t in the time domain, take a signal xt multiplied by t, the corresponding Laplace transform is minus dxs over ds, where xs is the Laplace transform of xt. Okay. Let us look at one last property, which is that of the integration, that is integration in time. Let us consider an integrator, for instance an integrator circuit which performs integration in time, and integration you can show that it is a low pass filter basically. Integration in time, or basically output of an integrator circuit, that is, let us consider xt which has Laplace transform xs. Then if you pass it through an integrator, the output is x tilde t equals minus infinity to t x of tau d tau. This is basically the output of an integrator circuit. And you can also show that acts as a low pass filter. This acts as a low pass filter. This acts as a low pass filter, and you can see that well, dx tilde t dt is equal to xt. That is, if I differentiate x tilde t, I get xt. Naturally, integration of xt gives x tilde t. So, if I differentiate x tilde t, I get xt. That is, differentiate the output of an integrator circuit, I get back the original signal. And if x tilde t has a Laplace transform x tilde s. Now, from the previous property, the derivative of x tilde t has Laplace transform s x tilde s, which basically must be equal to the Laplace transform of x of s, that is taking Laplace transform on both sides, because x t has Laplace transform x s, dx tilde dt must have Laplace transform s x tilde s, where x tilde s is a Laplace transform x tilde t, which means x tilde s has Laplace transform x s over s, okay, and the ROC will be the same. So, using the differentiation property, we have derived the Laplace transform of this, and the ROC will be the same. Okay. So, basically that wraps up some of these interesting properties. We have looked at the Laplace transform of some signals such as the cosine signal, and some interesting properties, important properties, such as what happens when you delay a signal, what happens to the Laplace transform, what happens when you take a linear combination of signals, and finally when you differentiate a signal and when you integrate a signal, what happens to the Laplace transform. There is one other important property of the Laplace transform, which is the convolution. What happens to the Laplace transform of the output of a convolution of two signals. We will look at that property in the subsequent modules. So, I will stop here. Thank you very much.